Alright, so we are going to take a look at some mechanics this time, just for a bit of fun. And we're going to study the following problem. We're going to take a look at, we're going to have a wooden stick, let's say a wooden stick attached to a base like this, and we're going to have a cylindrical magnet which is around here. I'm going to draw it the following way. So there's magnet 1, and another magnet here which is floating on top of that magnet, if you like. So these two magnets that I've drawn are cylindrical magnets. If we look down on them, we'd see a thing that looked like a donut. So magnetic material here, and they've got some thickness. Okay, and let's say they've got a total magnetic dipole moment m. So each one has a dipole moment m, little m, and they also have a mass big M. I'm going to write big M like this, and they're identical. And we've oriented them in such a way that the upper magnet is repelled by the lower magnet, and that the force on the upper magnet, due to the presence of the lower magnet, balances out gravity. So this one is floating. And we're going to ask a couple of questions about this. The first question we're going to ask is, what's the distance? How high does this thing float? All right, so what's the distance between these two? So let's call that distance z. And first thing we'll do is we'll solve for that distance. Okay, so in our model, we're going to model these two magnets as perfect dipoles. So we know we can write down the vector potential for a perfect dipole in the following way. So this describes the vector potential at position r due to a dipole of magnitude and direction little m located at position r prime. So in other words, let's draw that. Okay, so there it is. Here's our little dipole moment m. There's its magnitude and its direction located at r prime, and we're interested in the this formula gives us the dipole, the vector potential for that dipole at this position here. So what we really want is the magnetic field B, and we can calculate the magnetic field due to the magnets, or one of the magnets, by taking the curl of A. Now the formula that we've written here for the dipole moment is the most general formula for a dipole located at r prime. We're going to calculate first of all the field due to the lower magnet, and we're going to put that lower magnet, that perfect dipole, at the origin. So we'll specialize to that case. That means r prime is 0, and furthermore we're going to be interested in the magnetic field on the z-axis only. So what we would do then is we would place the dipole at the origin, the lower one, and we would take the curl of this equation and then look only on the z-axis. And if you do that, you'll get the following result. Okay, so just to re-emphasize the point here, this is the magnetic field on the z-axis due to the lower magnet, which I've located at the origin, right? And I'm assuming that the lower magnet, that both magnets have their dipole moment oriented in the z direction. So please go and derive this formula, start from this, put r prime equals 0, take its curl, and then look on the z-axis, and you should get this result. Okay, so the force on the upper dipole due to the magnetic field produced by the lower magnet is the following. Okay, so this is actually true in general. There's a discussion, a derivation in your textbook. I'm not going to repeat that here. So you can go and look that up. That's in the early part of the appropriate chapter in Griffiths. And we can use this equation to calculate the force on the upper magnet. Okay, so when I take that gradient, actually I generate a minus sign here, and that just tells me that I had the upper magnet oriented in the wrong direction. It would be attracted to the lower magnet. So if I were to flip that over, of course I could just flip that sign there just by changing the direction of M. So I'll just do that now. This is just to ensure that there is an upward force from the lower magnet on the upper magnet, and that that's going to balance gravity. Now I'm going to write this force here as, let's write this as F magnetic, and this is F magnetic, because there is another force, of course, on the upper magnet, and that is F gravitational. All right, and we are going to need to ensure that the total force on the upper magnet is 0. In other words, the upward force from the magnetic force it balances the gravitational force, and of course that gives us then the following equation. All right, so there's our equation then for the height that the upper magnet floats above the lower magnet. I'm going to introduce a new little symbol here. I'm going to call this Z. Let's call this Z0. So this is that particular location where the upper magnet floats above the lower magnet. Now, of course, what we should do here always when we get a formula like this is we should check the units. Now, I encourage you to go and check the units of that. I've checked the units. It is correct. The term on the right-hand side does indeed have units of length. So at least we know we're right up to constants like 3's and 2 pi's, and at least that's a start. So it's always a check you should make. Okay, so we're going to ask a second question here, which is kind of a fun question to ask. And let's return to our figure. We know we've got this stand here with our 2 magnets, and we know how high this upper magnet floats. This is Z0 defined on the previous page. But let's ask the following question. If I were to displace this magnet a small distance from its equilibrium position, it's Z0, then it's going to oscillate. It's going to oscillate upwards and down, up and down. And that oscillation will probably be damped, and we're not going to, the damping, we would need to put more information into this problem to calculate it, but we can calculate the oscillation frequency of this magnet. We're going to ask that question. What is the oscillation frequency of this magnet if we displace it for small displacements around the equilibrium position? And to do this, we're going to be interested in the force for small displacements, and we'll have to define small. So let's write down the total force on the upper magnet. Okay, so there's the total force. This is the magnetic bit. This is the gravitational piece. And you'll notice that I've written Z as Z0 plus delta Z. In other words, I'm writing this. I'm looking at small oscillations around a constant equilibrium position. Delta Z can be positive, meaning it's gone up above the equilibrium position, or it can be negative, meaning it's moved down. And delta Z now becomes our variable. Z0 is a constant in the problem. And what we're going to do is, what I hope by now is an obvious thing, we're going to expand this quantity for small displacements, where small means delta Z is small compared to Z0. All right, so let's take a look at that. What I've done here is I've factored out the large quantity Z0. I've got a Z0 to the minus 4. That leaves me with 1 plus a small quantity, delta Z on Z0. By assumption here, or construction, delta Z is small compared to Z0. And I've got the gravitational term here. Now I take the first order expansion, so the first order term in delta Z on Z0, and that becomes this term over here. So we get a 4 delta z on z0, or a minus 4 delta z on z0, a z0 to the minus 4, that's this one here, and then the constants 3 mu 0 m squared on 2 pi. And the 0th order term, of course, is this bit here, this 1, so all this. 3 mu 0 to 2 pi, m squared on z0 to the 4th, and I'm going to bring the mg over here because this term is precisely 0. Remember, this is actually the equation we solved. Which makes sense. The 0th order term at equilibrium should cancel, and we're just left with the first order restoring force term. There it is, and you'll notice that it's linear in delta z. Right? It's linear because we made a linear approximation, but that linearity, this is Hooke's law. This is the law for simple harmonic motion. So straight away we can extract an oscillation frequency from this, because we know that the law on the previous page is of this form. So there we go. All right, so our spring constant then, K, is given by the following formula. And we know that the oscillation frequency then is the following. Right, so there then are our results for the oscillation frequency. You'll see Z0 appearing here. Of course, we've solved for that earlier. And you see actually that the oscillation frequency in this case has quite a funny dependence on the mass and on the magnetic dipole moment, m. And the reason for that is that these quantities enter twice. They enter in the calculation of the equilibrium position, and then they enter again in terms of the calculation of the trapping frequency around this point. All right, now this is a very common procedure, which is why I wanted to do it and study a little bit of dynamics. It's very common in physics and in engineering that we look at oscillations around an equilibrium position, and we look for those oscillations for small displacements. So something you should realize is that if you have a bound system and the potential that's describing that bound system, right, so it's attractive potential, so it looks like a bowl if you like, that if that potential is differentiable, which in physics and engineering it nearly always is, that you can always make a harmonic approximation. You can always make a small displacement approximation which will give you a harmonic frequency. It's a very common procedure, and this is rather a nice simple example of such a calculation.